Okay, so we've talked about the band power trend. Let's talk about the power ratio analyzer. And we'll talk about technical details, clinical applications. We'll have an example. So when we talked about the band power analyzer, we took the different segments of EEG, we broke them up into their different frequency bands, and we plotted based on a specific frequency band exactly what we were going to see. So we plotted the alpha band, we plotted the delta band. And the difference with the power ratio is that we can now compare one to the other. In the alpha delta ratio, what we're actually doing is looking at the amount of alpha that there is and dividing that by the amount of delta that there is. And it's thought to be useful and maybe predictive of cerebral ischemia. Now, the technical details, if you look at the equation, it's essentially saying that the power is equal to the difference in our chosen frequency divided by the power for our second chosen frequency. Now, the way this works out is if you have alpha that equals the delta, your alpha delta ratio is 1. If you have more alpha than delta, then your alpha delta ratio is going to be greater than 1, larger number, because the numerator is larger than the denominator. If your alpha is less than delta, then you're going to have a low alpha delta ratio less than 1. I don't have a vasospasm example. The reference below is a published article on alpha delta ratio. Now, if I want to adjust things in the power ratio, there are a number of things that I can adjust. The numerator and the denominator frequencies. Now, what I've mentioned so far is alpha delta ratio, but you could select other ratios to do just by adjusting the numbers in the numerator and denominator. You could do the alpha beta ratio, comparing alpha and beta to delta and theta. You could compare beta to delta, beta to theta, et cetera, et cetera. Or you can choose numbers that are not necessarily our discrete frequency bands of delta, theta, alpha, and beta. You determine which electrodes are going to be included in the analysis, and the analysis time are the important parts. Again, I don't have a good vasospasm example, so I'm going to show you some triphasic waves. And this study, although it is not what alpha delta ratio would normally be used for, is interesting nonetheless. So I included the band power up at the top just for reference. So if you look at this example of triphasic waves, what you'll see is when I place the cursor early in the record, you see a significant amount of triphasic waves. And if you look at the band power up top, what you'll see is we've chosen 8 to 15 hertz on the upper part. We've chosen 2 to 4 hertz on the bottom part. So we're looking at kind of alpha range activity up top, delta range activity down at the bottom. And you can see that what we're seeing in the trends at the bottom, we see alpha delta ratio on the left and alpha delta ratio on the right. And in both cases, what you see is a low percentage of alpha in the left band power, and it picks up a little bit as you get towards the end of the study. So I'm just going to click on this, and you can see that this is primarily triphasic waves at the beginning of the study. And over here where the alpha activity picks up a little bit, we still see triphasic waves, but you see the entrance of alpha range activity in the study periodically. But I think it's interesting that this is something that you can see. So I'm going to close the band power trends here so that we can just look at the power ratio, and you'll see that these are pretty consistent with the minimal alpha activity early in the study and increased burst of alpha activity later in the study. There's something that's closely related that work has been done on as well. I don't have this trend exactly, but it's worth mentioning here. The percent alpha trend, or the alpha variability trend, looks at a overlapping frequency 6 to 14 hertz as the alpha, and the 1 to 20 hertz as the denominator. What Paul Vespa found is good alpha variability correlated with good cerebral blood flow, whereas poor alpha variability correlated with decreased cerebral blood flow. So if you look at it, what we're doing is we are comparing the alpha range activity to the entire range of other frequencies from 1 to 20 hertz. The measure that we're looking for here is not just a matter of the presence or absence of alpha, but whether it's variable. So it's partly objective, partly subjective. And so in the top, what you see is good variability, not just good alpha, because if you're in alpha coma, you would have alpha, but it wouldn't be variable. Conversely, if you're undergoing sleep-wake cycles, you are likely to have alpha that is quite variable. So this is a good measure of cycling in the brain activity. So you have good variability up top, poor variability up on the bottom, and this is typically correlated with decreased cerebral blood flow. Now, this is an example from Suzette LaRoche when she was at Emory, and this is an example over the course of about 10 hours. And you see in the upper example, you see the cursor is placed early in the study at about 6 p.m., where there is good variability, good significant amount of alpha, and the patient is actually awake and talking. And in the lower example, you see that the patient is unresponsive after vasospasm, and our cursor is placed out there somewhere close to midnight. Now, if you look at the raw EEG associated with these, without the trends, you see that there is increased slowing, less fast activity. But imagine you're a bedside nurse who's not trained to read EEG. Would you be able to recognize the differences in this EEG? If it occurred over the period of 4, 5, 6 hours, it would be very difficult to be able to compare these in any way. So that's one of the reasons that the alpha delta ratio or the alpha variability trends are very helpful, because they help identify, by compressing hours on one screen, they help you to identify those changes that occur more subtly and might otherwise be less noticeable. So again, tips on trending: no single trend stands alone for everybody. Use multiple trend types and optimize your data by customizing it, and the raw EEG is always the gold standard. If you can't see it in the raw EEG, it doesn't exist.